Hey there, guys. So far with matrices, we've done adding matrices, subtracting them. They have to be the same size. We've done multiplying a matrix by a scalar. We've done matrix multiplication. We've even done a bit of work on the powers of matrices as well. That was in the previous section. Now this is 9D, and in 9D we're solving systems of equations using matrices. Basically, we're solving simultaneous equations via a matrices method. Okay, so I'm just setting one of these up here. So this one is obviously a 2x2 matrix here. So we've got a 2x2 matrix. And then we've got a 2x1 matrix here. We can times them together because the 2 and the 2 is the same. We'll end up with a 2x1 matrix, or vector there if you want to call it that. And so this is a setup of an equation in terms of matrices. Now, in fact, normally, if you multiplied this out, you'd end up getting 2 times the x and 3 times the y, so you get 2x plus 3y, that's this times by this. You get 4x plus y as well, and that would go into your set of brackets giving you your 2x1 matrix. But in this question, we're being told that that's actually equal to 10, 6. So we can say that this must be equal to the 10. So we've got 2x plus the 3y equals to 10 there. And this must be equal to the 6. So we're getting 4x plus y is equal to 6. So this set of simultaneous equations is exactly the same as this equation set up in terms of matrices. Now you should be able to go definitely from the matrices to the simultaneous equations, but you should also be able to go from the simultaneous equations to the matrices. And you can see it's pretty straightforward, right? 2, 3, 4, and the 1 make your matrix there. And your x, y is what you're timesing by, and the 10, 6, what you're ending up with. Now you can do this with 3 unknowns if you want, but we're just going to do it with 2 unknowns to start off with. Okay, so if we look at the book, just have a quick look at the book. So they've come up with a couple of examples there as well. You can check those ones out. See how it's done in three dimensions as well, with S, T, and Z, they're calling them there. And after this comes a bit of chat, and you're welcome to read this one through. But the important point is it's saying, well, look, if A and B are the inverse of each other, then when you times an inverse function, or when you do a function of a function, the inverse function of a function, you should get back to the identity function. Okay, so basically they're talking about A being the undoing function for B and B being the undoing function for A. Now, as I said, with this thing at the bottom here, so like the one they've got there with the 10x minus 5y equals 35, what we're going to need to do is find a matrix which is the inverse of 10 minus 5 minus 3, 7. And if we apply that inverse to the left-hand side, then we'll get back to xy. But because this is an equation, we're going to need to apply the inverse to the right-hand side as well. So we're basically going to do an undoing matrix on both sides here to get back to xy. Okay, so there's the kind of the theory, but we basically want to know how this is working in practice. So they're suggesting here, just steal this thing here. So let's just take this bit here. So they're saying, well, look, if A and B are the inverse of each other, multiplicative inverse, that is, okay, so multiplication inverse, then when you apply AB, you should get 1, 0, 0, 1, the identity matrix. But likewise, if you do it the other way around, you should also get the identity matrix. So, we're looking like, like for example, x squared and the square root of x are the inverse functions of each other. So if you square something, you square 5, you get 25, you square root it, and you'll get back to 5. But likewise, if you started with 25 and square rooted it, you get 5, and when you square it, you get back to 25. So they undo each other. Okay, now they've set it up pretty nicely here because they've said, well, look, if this if this exists, it does in this case, then you should get this answer here. Okay, now we're going to take this into algebra, and we're going to take it. There's a really nice little investigation here, and they start to do this with part A to build you up to the algebra. But what I'm going to do is just take part B here, and it's saying, look, A is A, B, C, D as a matrix, and B is W, X, Y, Z as a matrix. Now, if they are the inverse of each other, then can you write one in terms of the other? In other words, if B is the inverse of A, can you write B, the W, the X, the Y, and the Z, all in terms of A, B, C, and D? And if you can do that, then you've got an inverse function which you can make from A, B, C, and D. Okay, so that's the plan. Now, if you want to skip this next part, you can, and you can go on to the next question, but I'm going to go through this a bit to show you why you end up with this rule down here. So if you look to the right-hand side, you'll see that we've got a to the minus 1 is this as a matrix. Now, a to the minus 1 there is talking about b above. B is the inverse function of a. So now we're writing it as a to the minus 1. And you can see where above we have b is w, x, y, and z. It's now all in terms of a, b, c, and d. Okay, now there's definitely stuff that you need to know about there. You need to know what the determinant is. You need to know some terminology there, and you can just look at this, and you can see this in the formula sheet as well. But if you want to skip on to the question, you're welcome to. But definitely also have a look at the formula booklet. So in the formula booklet, it tells you what the determinant of matrix is, and it tells you how to create the inverse of a matrix as well. And that's what's going to be used for the next question. Now, I'm just going to do a little bit of algebra for the next few minutes to actually develop this and to show you where it comes from, because it's not that difficult. Okay, so let's take a little bit here. And so let's set up those matrices. Let's call one A is A, B, C, and D. And let's call B its inverse. We're going to call this W, X, Y, and Z. And then when you times those two things together, well, let's actually do that. We're going to get A, W plus B, X, plus B, Y. And then we'll get A, X plus B, Z, because that's just this times this, and sum them together. And then, of course, we're going to get CW plus DY, and then we'll get CX plus DZ. Okay, so that's the multiplication of A and B. That's A and B. But what we want, for these to be in the inverse of each other, we want to get out 1, 0, 0, 1. Okay, so that's our identity matrix of order 2. That's I2. Okay, so now we can turn these into a set of simultaneous equations. So we've got, in fact, 4 sets of simultaneous equations. We've got AWBY equals 1. We've got CW plus BY equals 0. So I'm just equating these things to these things here. Of course, we can come up with 2 more equations by setting these things equal to this and this as well. Okay, now I'm not going to write down the other 2 because I'm only going to do one of these parts here. But if we're going to solve this set of simultaneous equations, let's try dividing this one by B, this one by D. So there's 1, there's 2. And so we're going to get A over BW plus Y equals 1 over B. And in the second line, we're going to get C over DW plus W back W plus Y equals 0 over D. 0 over D is, of course, just 0. Now, if we're going to subtract these lines from each other, okay, so we take the second one away from the first one now, we'll end up getting our A, B minus C, D lots of W. And the y's are going to cancel, and that's going to be equal to 1 over b. Now, I can take that a bit further by combining the two fractions here. So I'll get AD minus BC over BD, lots of W, is equal to, and let's make a common denominator on the other side as well. Let's make BD over 1. And now you can times both sides by BD and divide by the AD minus BC, and we're going to get W is equal to 1 over AD minus BC. Okay, so that's W, and you can go through the same process for X, for Y, and for Z as well. Okay, now when you put all of those things together, you're going to get, there we go, you're going to get, sorry, not that, you're going to get this A to the minus 1 here is equaling to your B. I think it's probably better done in the book here. So let's have a look at the book. So they've come up with this now. Let's just take this thing here. Okay, and this is basically what your formula booklet is also telling you. So let's look again at the formula booklet. Formula booklet has here in the final vector, it says, in the final matrix, it says D minus B and minus C and A, 1 over the determinant of A at the front there. Now, it's also put the condition AD is not equal to BC, and that's because the determinant can't be equal to 0 itself. The determinant is equal to AD minus BC. Now, again, we look at this thing here, and you can see all they've done is they've factorized out this thing here. So they've said, well, this thing is equal to 1 over AD minus BC, and we're left inside with the A and the D swap around from our original matrix. So that's D and A. And the B and the C stay where they are, but they you take the negative of both of those things. And we factorized out this thing here. Now, this thing on the bottom, because it's used so much, we can write as 1 over the modulus brackets of A. So then we've got our matrix inside B minus C and A. Okay, and A. So this on the bottom with modulus brackets is normally written with a capital A and a bold A in the books as well. We can just write it as a capital A with the modulus brackets around. That's just equal to AD minus BC. That should be pretty obvious from what I'm saying there. Okay, so this is how to make an inverse matrix for a 2x2 matrix. Now, you are expected to be able to do this and do this using the formula given to you in the formula booklet. You are not expected to do this for a 3x3 matrix or a system of 3 simultaneous equations. But you are expected to be able to do that using your GDC, using your calculator for that one as well. Okay, now I'm going to have to stop there because I've got a lesson, and I'll do example 3 and tag it on to this one after my lesson. Okay, thanks guys, and I'll see you back for the next bit after this. Hi there guys, well, welcome back. So we're now working on some of these examples. Example 3 says find the inverse of this matrix here. Obviously the inverse matrix is going to be useful for solving sets of simultaneous equations disguised as matrices. But in this case, they just want the inverse function or the inverse matrix. And then there's one which uses technology, and there's a couple more questions after as well. So let's look at this first one. And this first one can be done purely by going to the formula booklet and getting out this formula here. So this is the determinant. So we can work that one out. Let's do that first. The determinant is equal to AD. So let's set up A, the original one, A, B, C, D. So AD is these two things times together. It's getting -4 there. and then minus BC, so minus these two times together. So that's going to give us minus 6. So that's going to give us plus 6 there, so that's 2. So our a to the minus 1 is equal to 1 over 2, and then we've got d minus 4, and d and a swap around, so a is going to go there, and minus b is going to give 2, and minus c is going to give minus 3. So there's a to the minus 1, that's the inverse function. It's really straightforward, it's a set of substitutions to do. We can obviously incorporate the half inside as well. It depends on how they want us to write it out, but I think I would want to write it as a single matrix anyway. Though there's nothing wrong with that answer, we would probably want to put it as a single matrix to make it really clear. So we've got minus 4 divided by 2, so we've got there minus 2. Half times 2 gives us 1. Half times the 3, minus 3 gives us minus 3. 2, we could leave that as an improper fraction, no problem. And then we've got a half in this corner as well. That's just 1 divided by 2 or times by a half there as well. So half there as well. So there you go. That's a to the minus 1. Now, of course, if you did a to the minus 1 now times by a, you're going to get back to your identity matrix, which we talked about before. Okay, let's look at the next one. Example 4. Says use technology to determine the inverse of this, and we've got a 3 by 3 matrix here. Again, we're not being asked to solve a set of simultaneous equations just yet, but for examples greater than 2 by 2, we can do this using technology. That is fine for our course. So it's really straightforward to do in your calculator. You can simply type in your matrix and put to the minus 1, to the power of minus 1 on the outside, and it will give you your matrix. Now, you can verify that p times by p to the minus 1, or p to the minus 1 times p gives you the identity matrix of order 3 simply by putting those into your calculator. Let's just check that one. So let's see what they're doing. Okay, so just clicked on the calculator button there for this question, and you can see this is the TI Inspire version. So you can create a matrix, and this is pretty neat here as well. We can say we can store this as something too. So although you could do to the minus 1, storing something is rather useful. So you can store your matrix now that you've made it as P by saying control and then pressing the VAR button and then going to store. So whatever calculator you use, learn to store this, because then you can do P to the minus 1. And you can use that later on, of course, as well to verify. When you do P times P to the minus 1, that will be really straightforward to do because you've defined your matrix. Okay, so that's a useful tip there. Okay, let's look back in the book, see what else we've got. So after that question, here we go. This is essentially the algebra at the top here behind why this is now going to give us our set of solutions. So if we've got AX is equal to B, so that's like setting up, I don't know, 2, 3, 1, 4, X, Y equals 10, 6, keep coming up with 10, 6. That would be our matrix B, this would be our matrix A, this would be capital X would be our matrix XY, or we could call that a vector as well. So we want to undo this. So to undo this, we'd need to use a to the minus 1, which is what we've been trying to work out. Of course, if we do it to one side, we're going to need to do it to the other side as well. So we're going to need to put it in there as well. Once you've done that, a to the minus 1 of a is going to give you your identity matrix. So that will just bring us back to our x. In this case, the matrix x is x, y. And then you'll end up with a to the minus 1 of the thing on this side. Okay, so if we can find a to the minus 1, we just need to apply that to b for the thing on this side. Okay, so again, let's have a look at the question here. So they do this longhand for part A, because it's a set of two simultaneous equations here. And for part B, they do it via a calculator. So you use a calculator method for that one. So for part A, you can see, let's just take this again, through it. Okay, so for part A, here we go. You can see that they're, first of all, saying this and this, these things are both equivalent. So it's your set of equations, which can be written in a matrix format. And then we've got a to the minus 1, so that's our A if you like. A to the minus 1 is what we need to find out, so we're just stating that for the examiner there. We're going to apply it to the other side as well. And at that point, we know that these two things are going to become our identity matrix. That's there. And now we actually need to work out what this is, and that's via the same process as we did in the previous question. So swap these two things here, take the negatives of these two things here, so doing it, take the negative of these two things here, swap these two things here, and then do 1 divided by your discriminant as well. Discriminant being these two times together, take away these two times together. That's obviously from your formula booklet. You can simply use that from your formula booklet. Okay, once you've got that, you can now do your matrix multiplication here and divide by 1 over, times by 1 over 55, or divide by 55, both of the elements which end up in your matrix. So, you can times those two together and then probably do your division afterwards. So we're getting this as our answer, and then incorporate the 1 over 55 into your vector. And then when you do that, you'll see that x is equal to this and y is equal to this. That's the solution to this set of simultaneous equations. Now, obviously, you have faster algebraic methods of doing this, but and you also have this on your calculator as well. So everyone has solved sets of simultaneous equations on their calculators, on their GDCs as well. But now we have a matrix method to do it on our calculators too. Okay, if we look at the next one, having a look at the next one, again, we can set up our three simultaneous equations with three unknowns in the following way. The 0 minus 6, 2 can be our final matrix answer. And then just the same as before, we can do the inverse matrix of A, apply that to both sides. Frankly, we don't need to write that down on both sides because we've already undone it on the left-hand side. So now we apply the inverse matrix to 0, minus 6, and 2. Of course, you can do that one on your calculator, and it's giving the line underneath. That should really say equals 2. And then, of course, you can state your solutions for S, T, and Z. Okay, so that's good, and that's done, and you can get on with the exercises now. However, there's a little, excuse me, there's a little extra bit here on the applications to cryptography, which is pretty nice. Again, you can read this at your own pace if you wish to, but just to talk about it very briefly, they're saying, look, here's a bank account password, Charlie 578 Sam star and exclamation mark, asterisk, in fact, exclamation mark. Okay, and so then we've got a whole load of numbers which are associated with our symbols. And so we're saying, well, the password, the original password can be changed into those numerical numbers just using the code table, which is above. And then you can encrypt that by using a matrix encryption. So you could change this password, where there's 15 letters there, you could change that into a 3x5 matrix. It's up to you how you wish to do that, or up to the bank rather, as to how they wish to do that. But in this case, they're choosing to split that into a 3x5 matrix, because there's 15 numbers there, and the way in which they're doing it is putting 29, 8, and 1 into the first vector, if you like, and then combining them as an entire matrix there. Okay, and then to encode a message, you can then choose any 3x3 matrix, and you can apply that encryption cipher, which they're calling C, to your message. So you're doing C times by M, and that's going to give you a new 3x5 matrix. And so then that is that combines with the cipher. So the bank will have that cipher matrix. You put in your password, it combines with the cipher, and it gives you out this matrix at the end, this new 3x5 matrix. And the bank recognizes that and says, okay, well, we accept you in here because this matches. Okay, but you can decrypt this as well. So you can undo that now coded message, okay, by doing C to the -1 of this encrypted message. Okay, so if we wanted to go back and find what the password was from the encrypted message, you can do to decrypt the password, to hack it if you like, we can do C to the -1, so the inverse cipher, which will take us back to the original message. So inverse cipher in this case, they're just saying that 3x3 matrix to the power -1, actually writing down what it is underneath, apply it to your encrypted message, and you will get back to your original password, which is of course in code still there, it's still in the numerical versions, but then we can turn that into letters afterwards as well. So there's a possibility for encrypting and decrypting messages using matrices. Okay, so 9D is question 1 through to question 7. No, question 8, in fact. There's a lot of practice to get here. This is pretty difficult stuff, as you can see by quite a long video again. Take your time with this, get lots of practice. This is really crucial stuff. So yeah, get lots of practice. Thanks for listening today, guys, and I'll see you later.